So now we're ready to look at some specific examples of testing a claim about two sample proportions. So this is the same slide that we ended with in the last lecture. Summarizes all of the variables that we're going to be working with. It summarizes all of the both of the requirements, right? And these are really the same requirements that we had when we were working with a single sample. Only now, right, we're going to require that the two samples have to be independent, and we have kind of this size requirement down here, item number 2, and that applies to both samples. Okay, and finally, we've got our formula for our test statistic. Right, that's this kind of messy thing right here. And you notice I'm referring to this as Z. Okay, and that's because just like with everything else we've done when we were talking about proportions, right? Everything we do here when we're talking about proportions from two samples is going to be based on z-scores and normal distributions. All right, so I have here the same example that I used to illustrate the concept in the previous lecture. Now we have the tools that we need to actually answer the question. All right, so we have a school teacher, and she has learned this new method, and she wants to test its effectiveness. All right, so she has her results from last year when she used the old method, and she wants to compare those to her results from this year. So we have two proportions, and we want to test to see if there's a difference. Well, first, let's check our requirements, right? It's reasonable to assume that this year's students are independent from last year's students. Usually, this is something. This is a good example of a situation where you need to be aware of what's going on in your sample. If the teacher had a student, for example, who was repeating the grade, then they presumably learned last year with the old method, even if it was from another teacher, and even if they learned with a third method, that prior exposure is going to potentially make it easier for them to learn the material and could skew the results. So the simplest solution would be just to exclude that particular child's result from the sample. So we're going to assume that we do have independence here, and let's look at our successes and failures. In her current class, she had 12 successes out of 20. That means there were 8 failures. That's 5, at least 5 of each. And last year, she had 10 successes out of 19. So that would be 10 successes, 9 failures, which is also at least 5 of each. So our requirements are met. All right, so now I know that what I need to do is come up with my test statistic. But first, let's be clear what we're looking for. The claim here is that the new method is better than old. Okay, so what are our two hypotheses? Well, our null hypothesis is always that the two proportions are equal, right? And our alternative hypothesis will be that the new method is better, which you note, right, matches the language of the claim. All right, so now what we need to do is calculate our test statistic. So our test statistic, and let me note here, right, this is a z-score we're finding. That is p1 hat minus p2 hat divided by the square root of p bar q bar over n1 plus p bar q bar over n2. So now I know all the pieces that I need. I need to know p1 hat and n1. I need to know p2 hat and n2. And finally, I'm going to need p bar and Q bar. All right, so P1 hat, that is the current class. That was 12 successes out of 20, which is exactly 0.6. And our sample size here was 20 students. P2 hat, that is the previous year, so that's 10 out of 19, which is 0.5263, and sample size is 19. All right, so P hat, remember this is x1 plus x2 divided by n1 plus n2. So let's see, 12 plus 10 divided by 20 plus 19. That comes out to 0.5641. Q bar, that is 1 minus P bar, which is 0.3214. Okay. Oh, excuse me. Sorry, I was jumping ahead in my notes here. That is 1 minus 0.5641. That's 4.4359. Now, it's just dropping all these numbers into this formula and being really super careful with your calculator. All right, so let's see. This is 0.6 minus 0.5263 divided by 0.5641 times 0.4359 divided by, let's see, make sure I get this right now, N1, that's 20 plus, and I really am running out of room here, so I'm gonna shortchange this a little. It's this expression again divided by 19. All right, so put these numbers into your calculator, and you get 0.4638. That is our test statistic. So next step, find the p-value, right? The p-value is the probability z is greater than 0.4638. Remember, go back to the null hypothesis. The null hypothesis said greater than. So this is a right-tailed test, which is why I'm doing a greater than probability here, right? And again, right, go to your calculator or the table. This is 0.3214. All right, so that is the p-value. Remember, what was our significance level right here? Alpha is 0.05. Right, so this is greater than our alpha value, which means the likelihood that the variation we're seeing between the two samples occurred by chance is pretty likely, right? That's a fairly high number. So there is no evidence to support rejecting the null hypothesis. Remember, I like to try to just take this into plain English for just a minute. In English, that means we like the null hypothesis, right? Which says that the results were the same, which is the opposite of the claim, i.e. we don't like the claim. So my conclusion would be that there is insufficient evidence to support the claim that the new method is producing better results. Okay, so now if we take a step back, right, and do just a quick reality check, the final results here and here, the proportion of successes were pretty similar, right? Only about, well, I compare that to p-bar, excuse me, 0.5263 to 0.6. They're pretty similar. They're only about 8 percentage points different. Under some circumstances, that might have been enough, right? But it wasn't, considering our relatively small sample sizes. So if the teacher wasn't satisfied with the results, right, if for some reason you wanted to continue to test because the results were so close, one approach could be to use the method again in the following year and then combine the 2 years, right? The 2 years with the new method together into one sample, and use 2 prior years with the old method for comparison. So we've got another example here for us to practice with. I mean, you can take a look at this, pause if you like, and see if you can work this out on your own. Then you can start up again and go over my solution. All right, so we have 2 machines here, and they're both producing high precision parts, and they do have a certain failure rate, and we want to compare them. So what I'm asking here is, are these 2 machines in sync? Are they each getting the same level of results? So first, our claim is that the machines are the same. They're getting the same results. Our null hypothesis is what it always is. P1 is equal to P2. And for my alternative hypothesis, all I care is that they're different. It doesn't matter to me if one is greater or less than the other. All I need to know is, are they in sync, producing the same level of quality, or are they not? Okay, so in testing our requirements, right, independence we're squared away on. There's no reason to believe that one machine is somehow affecting the other. And our minimum size requirements are both met, although it's a close thing. The first machine just has 5, and the rule is at least 5. So, okay, that one was right on the edge, but it made it. And 7 is, of course, greater than 5, so we're squared away there as well. Okay, so let's find our pH, our individual values here. P1 hat we need, and we need N1. And we're going to need P2 hat and N2, and then P bar and Q bar. All right, P1 hat, that is 5 divided by 200, which is 0.0250. Sample size there was 200. P2 hat, this is 7 divided by 300, which is 0.0233. Sample size here was 300. Now, for Q bar, this is 5 plus 7, the grand total successes, divided by 200 plus 300, which is 0.0240. Q bar, it's 1 minus P bar, so this is 0.9760. And that's it. Those are all of our values. So now we can calculate the test statistic. Remember, that's our kind of messy formula here. It's P1 hat minus P2 hat divided by square root P bar Q bar over N1 plus P bar Q bar over N2 square root. I'm just going to do 1/2 power, right? That's the same as a square root. It's a little easier to write. All right, so let's get our numbers in here. This is 0.0250 minus 0.0233 divided by square root, should I get the right numbers now, 0.0240 times 0.9760 over N1, that's 200, plus, and again, I'm going to get a little lazy, it's this same product here, divided by 300, square root of the whole thing. Now you go to your calculator. This is 0.1193. And remember, we're doing a two-sided test, right? So for my p-value, I need the absolute value of z is greater than 0.1193. Now you remember what if I just draw a quick sketch here, just refresh your memory. Right, we have our normal curve. We have 0.1193 up here and negative 0.1193 down here, and we want the total area in the tails. So the table tells me that left-hand area, if you look up negative 0.1193, right, you get 0.4525, and I'm just going to double that because the right-hand tail is the same size. So this is 0.9050. Now, that is greater than our alpha value, which means the likelihood that the variation we're seeing between the two samples is likely to have occurred by chance. So there is no evidence to support rejecting the null hypothesis. In English, I like to do this, just think in English for just a minute instead of statistics. We like the null hypothesis, which says that the results were the same, which is the same as the claim. That is that we like the claim, right? So my conclusion would be, and I know this is the tricky one because the language just gets a little awkward, but I would say that there is not sufficient evidence to warrant rejecting the claim that the two machines are producing the same results. Or again, in plain English, we are pretty confident that the double negative in there just gets weird, right? It is the technically correct way to say it, but in practical terms, we are reasonably confident that the two results we're seeing are going to be the same. I know it's not the technical way to say it, but if you're going into a boardroom, board of directors, CEO of the company, ultimately you're going to have to give this to them in language that they can understand. Okay, so what's next? Well, we're going to kind of do the obvious thing, right? Now that we've done this with proportions, we're going to see how we would go about doing this with means. And again, it's going to be very, very similar, right? All that really is going to be different. It's going to be just some tweaking of the requirements and a new formula for finding the test statistic.